As we get into these multiple angles, I know they're a little bit tricky, so I went ahead and decided I'd go ahead and do some reviewing of those double angles before we start into the second half of this, which is the half angles. Let's look at some double angles. Just this particular example is verifying. Make sure that the left side equals the right side. Looking at it, it's kind of messy looking. Tempting to look at this as though it's a Pythagorean identity, but that should be a plus sign if that were the case. Not going to be able to do that. Got a lot of different trig functions in here. Let's go sines and cosines and everything, which means for the cosine of 2x, I'm going to convert that to a cosine squared x minus sine squared x. On the left side, we're really going to have a mess because we're going to have fractions caught up inside of fractions. That's all right. Here we go. 1 minus, this is going to be sine squared x over cosine squared x. That's going to be all over this secant squared x that we have, which I'm probably going to end up bumping up and calling it a cosine squared. But before I even do that, I can look at this 1 minus sine squared cosine squared. I'm going to convert that into having a common denominator instead, like thinking of it 1 over 1, but I'm going to call it cosine squared x over cosine squared x. Now I can subtract those. And again, I'm going to leave that secant squared alone on the bottom for right now, and I'm going to have a cosine squared x minus sine squared x. Notice this over here. I think I'm going to be able to do something there. Over the common denominator cosine squared x. Now that's all over secant squared, right? Well, what I'm going to do is I'm going to bring that secant squared up, and I'm going to call it a cosine squared. Remember, you can bring that up. So I'm going to undo what I just wrote there and bring the secant squared up and call it a cosine. Now when I bring it up, it's now part like cosine squared over 1. Remember where we're headed over here to look like this, which we're pretty much right there. Those cosine squareds are going to cancel, and we've verified that identity. Again, I boxed that in, but the real answer is all of this work prior to that. Let's try another one. Going to verify again, but I thought it would be good to throw something kind of crazy in there, like a cosecant double angle. Well, I don't have a double angle identity for cosecant. You just have to remember that cosecant is the reciprocal of sine. I can just use my sine identity. This 2 that's out in front is like a 2. I'm going to go ahead and put it over 1 because I know I'm going to be turning stuff into fractions. The cosecant double angle is really just 1 over the sine double angle. And tangent x is sine x over cosine x. And somehow or the other, that's all going to equal secant squared x. And I could leave that secant squared x, but if I look over here, everything is sines and cosines. I think I would probably benefit by calling that 1 over cosine squared x. Now let's look and see what happens. 2's cancel, sines cancel, and I have a 1 over cosine squared x. And I kind of did that all in one step. These look scary to begin with, but there's really not too much to them once you throw that double angle identity out there. We're going to try a solving problem here that uses a double angle, and I thought I'd try it. I'm showing you one that maybe is a different strategy than what we've had to use before. First of all, it's a double angle that includes tangent, and it may be tempting to look at this and try to factor a tangent x out, but you can't really do that. This is the tangent of a particular angle. This is the tangent of a different angle entirely. You can't just factor it out and like leave a 2 or something. It doesn't work like that. Your first step is always to get rid of that double angle. So let's use that identity that we have for double angles. For tangent, that would be replaced with a 2 tangent x over 1 minus tangent squared x. Before I add the tangent x, what I see happening here is having to write tangent over 1, get a common denominator, and multiply this and get it all put back together. Here's a different strategy. Because I only have the two terms, what I might want to do is move the tangent x to the other side of the equation, which is going to end up giving me a negative tangent x. It's not a fraction. I'm going to put it over 1. What this gains for me is a fraction equal to another fraction. That's just a proportion. And way back in middle school, you learned how to solve proportions. You can just do cross products. I'm going to try that method to solve this equation. Let's do cross products. 2 tangent theta, or tangent x, is equal to, now when I do, that was this direction. Now when I go this direction, I have to look at this as though it's in parentheses, and I'm going to be distributing my negative tangent x through that. That would get me a negative tangent x plus tangent cubed x. That looks a little bit, we have a cube, we don't have that typically, so that's a little bit different. But I do have this tangent x and this other tangent x term. I think those could combine together. I'm going to go ahead and subtract the 2 tangent x to this side. And I'm going to end up with a 0 equals negative 3 tangent x plus tangent cubed x. Now, since I'm doing the tangent of an x and the tangent of an x, I can pull out a GCF. Let's go ahead and pull the tangent x out, and in parentheses I would be left with a negative 3 plus tangent squared x. And we'll set each of those equal to 0. Tangent x equals 0, and then on this second part, I'm going to add the 3 over, and then I'll square root both sides, which will leave me with a tangent x equals plus or minus root 3. Now let's take those two answers, and I'm going to drag them up here where I have a little bit more space. Tangent x equals 0. Where does that happen? Well, tangent is 0 at 0 and at pi. Notice that I'm solving from 0 to 2 pi. I don't need the plus 2 pi in business going on. The second part of this, all right, so that's one of my answers, or one set of answers. The other part of this, tangent x equals a plus or minus root 3, that happens at all of the pi over 3's. And since it's a plus or minus, it's all 4 quadrants. I'm going to have x equal to pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. That's the other set of answers. This proportion idea works really nice if you just have 2 terms. And then you move one term over there, and then you can set up your proportions. Let's finally get started on the new, or the second part of 5.4 of the multiple angle identities. We did the double angles. Now what we're going to look at are half angles. Instead of looking at the sine of, let's say, of a 30-degree angle, so sine of theta might be 30, we're going to be comparing that to a 15, because we're going to take the 30 and divide it by 2. This is going to allow me to find the sine of a 15-degree angle, which wouldn't normally be something I can do because it's not on the unit circle. Notice that this would be 30 divided by 2, and I'd be using the 30 within the identity, and that's something off the unit circle. The one thing that I want to draw your attention to before we jump in and do these, this plus or minus that's in front of these identities, that doesn't mean that it could be positive or negative. It is. It's either positive or negative, but you have to make the decision on whether this particular half angle would be positive or if it would be negative. You'll have to determine what quadrant that half angle, not the theta, but the half angle, decide what quadrant that's in, and then make a decision if it's positive or negative. Don't always just put a plus or minus. The other thing, notice that tangent has two options there. You use whichever one is most helpful at that time. And as always, I'm going to start and look at something with numbers. To determine the angle value to use in the formula, you must take the angle value that you're looking for and you multiply it by 2. And then you're going to take that and write it as a half angle. For instance, if I'm looking for a 67.5 degree angle, I'm going to double that, which gets you the 135. That's going to be the theta. And then you write it as theta over 2, which really is just 67.5. We've just written it a different way. By writing this way, we can recognize that this is the theta that we'll be using in our identity. It happens to be something off the unit circle. If they ask me to do a 22.5, well, we're going to write it as a half angle. We're going to write 22.5 as double it, divide it by 2. That's 22.5. That's how I'm going to write it. Here's one. Let's try it with radians. Always trickier with radians. If you're asked to find pi over 4, pi over 4 is half of pi over 2. I'm going to write it as pi over 2 divided by 2. And then this will be the theta that I use in my identity. For example, let's try some. This one's 6. We want to find the sine of a 22.5 degree angle. And it seems like that would be no special angle whatsoever, but it does happen to be half of a 45. That means I could figure this out using my half angle identity, and I can find it out exact, not as a decimal. I'm going to use my sine identity. And remember that I'm going to find the sine of not a 22.5, but a 45 divided by 2. That's how I'm going to write it. That tells me that 45 is the theta that I'm going to be using in my identity. The identity for the half angle is a plus or minus. Let's come back to that in a second. Let's go ahead and write the rest of this. 1 minus the cosine of theta. Remember, theta is this right here. That's the thing that I know off of the unit circle, all over 2. Now let's decide on this plus or minus. You look at the half angle. This whole thing, not the 45, but the 45 divided by 2, the 22.5. That would be in the first quadrant. Sine in the first quadrant is positive. I'm going to put a plus sign here. Not that because we really need that, but just so that we've acknowledged we have decided it's positive. Now let's just simplify the radical up. It's going to be a positive. Square root of 1 minus, the cosine of 45 is root 2 over 2. So I'm going to change my 1 to a 2 over 2. And then all of that is over 2. That's a mess of stuff. This is really going to be, more than anything, practice working with radicals, review of our algebra skills. Typically what I do with this divide by 2 is I'm going to bring it up and I'm going to call it a times 1/2, multiplying by the reciprocal. But I am going to go ahead and simplify this part first, and then I'll bring it up. Might be good to start making bigger square roots, huh? I'm going to have a 2 minus root 2 over the common denominator of 2. And then when I bring the 2 up, it's going to be multiplied by 1/2. I end up with 2 minus root 2 all over 4. Oops, that's not a minus, sorry. It's just a positive. Big square root. Remember that you can square root your numerator and denominator individually. I'm going to end up with a square root of 2 minus root 2, which is messy, having radicals caught up inside of radicals, but it will happen and we just leave it. All over, the square root of 4 actually comes out nice as a 2. And it is positive. If you want to keep that positive sitting there, you can do that. Final answer, a positive square root of 2 minus root 2 all over 2. Not necessarily pretty, but it is exact. Let's try again. Number 7 here is the tangent of pi over 12. Your first step is to go ahead and rewrite that pi over 12 as a fraction. Go ahead and double it, which would be a pi over 6. And then put it over 2 to go back to the pi over 12. We write it that way so that you recognize that this is the theta in the identity. Tangent has a couple options for us. To be honest, I kind of prefer the one that has a monomial for my denominator. I'm going to use 1 minus cosine theta. Well, theta is pi over 6 all over sine of theta, which is pi over 6. There's no radical. That makes it a little bit nicer. Let's start evaluating from the unit circle. I'm going to have 1 minus the cosine at pi over 6. That's your long leg, root 3 over 2. I'm going to change this to 2 over 2. I do this about every time. All over, now what's the sine at pi over 6? Well, that's your short leg. You're up a half. On the tangent, you don't have to worry about the positive or negative. The unit circle values that you're plugging in will take care of that. I'm going to do a couple things here. I'm going to merge that numerator and I'm going to bring my 1/2 up and multiply by the reciprocal. I end up with a 2 minus root 3 over my common denominator of 2 multiplied by the reciprocal, which is 2 over 1. How nice is that? Final answer, 2 minus root 3. And that's the exact value of a pi over 12 angle, tangent of a pi over 12 angle. All right, this one is for you to try on your own. It's a cosine of a 105. I'm going to get you started and then I'm turning you loose. This is going to be rewritten as the cosine of not 105, but 210 divided by 2. Now you know that this is the theta that you will use in your identity. All right, you give it a shot. Pause the video. Okay, check out my answer. Do you agree with that? Hopefully so. Real quick, one thing that I did is I made this negative because 105 is in the second quadrant and cosine is negative in the second quadrant. You can see I'm just pulling numbers from the unit circle here, and at the very last step I end up with a square root of this over a square root of 4. The square root of 4 is just 2. Notice I don't have a radical on that 2 anymore because it was a square root of 4. The last type of problem that we have are those ones that aren't on the unit circle and we have to draw triangles for. In this particular example, I've given you the cosecant of u. And I am telling you that u falls between pi and 3 pi over 2. That's basically telling you what quadrant to draw your triangle. My triangle is going to fall in the third quadrant, so I draw from the origin straight back up to the x-axis so you get your right angle, and stick your angle measurement in there. That's a u. Sorry, that kind of looks like a 9. Let me rewrite that. Your u is up there by the x-axis. Cosecant, maybe you don't really remember cosecant, but you should know that sine is the reciprocal of that. So when cosecant is 3 or 5/3, sine is going to be 3/5. It will still be negative. So you'll have a negative somewhere on there. Come over to your triangle. Sine is opposite over hypotenuse. One of those needs to be negative. Since you're going down, the 3 is negative. Recall that the hypotenuse is always 5. I'm sorry, is always positive. Another nice little Pythagorean triple. They do tend to be nice about giving you Pythagorean triples on this. Not always, but you know, sometimes. That's going to end up being a 4. It's to the left. You'll make it a negative 4. Once you have all the sides filled in, you should be able to use your identities to evaluate your half angles. In other words, we're looking at what is half of this angle. Well, I know that if it falls in the third quadrant, if I were to take half of it, it would fall somewhere in the second quadrant. Think about that, because I'm going to have to do my plus or minus on sine and cosine, and know that the half angle would end up in the second quadrant. The half angle then for sine would end up being positive. Let's keep that in mind. But the half angle for cosine would end up negative, and we don't have to decide on the tangent. The identity takes care of it. For part A, the sine of half of u, notice we don't really even know what u by itself is, what angle measurement that is, but it doesn't matter. We're just looking for relationships now. It's going to end up being a positive, we decided. Square root of 1 minus the cosine of u. The cosine of u is what would be adjacent over hypotenuse, and that's all over 2. These come out a little bit nicer because everything's going to be a fraction, a nice fraction. No radicals, you just work through the numbers. This is going to end up being a positive. Big square root. I'm going to write this as a 5 over 5 plus 4/5. And instead of dividing it by 2, I'm going to bring it up and multiply it by a 1/2. That ends up getting us, we'd have 9/5, but if I take half of it, it's going to be 9/10. When I square root that, and again, it's positive, and if you want to keep writing that positive sign, that's fine. It's not a big deal since it's positive. This becomes 3 over root 10, which when you rationalize it will be 3 root 10 over 10. Let's try again with the cosine. Very, very similar. Cosine of your half angle. We've already decided cosine in the second quadrant. Remember, the half angle would fall in the second quadrant. Will be negative. I'll have to make sure I keep that there the whole time. And then right here, instead of 1 minus cosine, it's going to be 1 plus the cosine. And the cosine was negative 4 over 5. And that's all over 2. Negative. Big square root. I'm going to write that as a 5 over 5 minus 4 over 5. Instead of dividing by 2, I'm going to multiply it by 1/2. I end up with a 5 minus 4, that's 1/5, times 1/2 is 1/10. The square root of 1/10 is 1 over root 10, which is the equivalent of root 10 over 10. Oh, what'd I forget? Look at me. I started losing that negative. That's why I tend to write the positive, because I have this tendency to lose that sign, so I make such a point of it, and there I went off and forgot it. Negative root 10 over 10. Tangent of u over 2, or of your half angle. You can use either one. Again, I kind of like the one that has the monomial in the denominator. I'm going to do 1 minus the cosine of u over the sine of u. That's the one I'm going to use. I'm going to end up with a 1 minus the cosine, we've done every time, is negative 4 over 5. And that's going to end up over the sine of u, opposite over hypotenuse, is negative 3/5. I'm going to call my 1 a 5 over 5. 5/5, this is going to turn into plus 4/5, is going to turn into 9/5. And instead of dividing by the negative 3/5, I'm going to multiply by the reciprocal. That reduces real nicely. The 5's cancel, the 3 and the 9 reduce. Looks like it's going to end up being a negative 3. Who'd have thought that would have come out quite so nice? All right, there's your half angles for you. Hope this helps.